Hi everyone, my name is Chengwei Cai. This is my video presentation for my final year project. My final year project is about Polar code in C implementation. In this video, I will go through the following points. Firstly, I will give an executive summary, which will include an introduction to my project, the objectives of my project, the main concept behind it, and also I will show some examples of the outcomes. After that, I will go deep into what I've done in this project. I will analyze step by step, and I tell you what I've achieved. And also at the end, I will show all the outcomes, all the results I got from the simulation, and I will give in conclusion as well. So what is for Polar code? First things first, we go back to the original problem. For example, if there is a noisy channel and we like to send some bits through this channel, at which rate the information bit can be reliably transmitted over this channel is called channel capacity. So basically for every channel, every noisy channel, there will be a channel capacity, there will be a limit. We like to achieve that limit. Polar code is a linear error correction code. It was proposed by Adel Arakant in 2008. Theoretically, it can achieve channel capacity. Huawei, one of the leading mobile wireless technology company, they've announced that they've reached 27 Gbps downlink in using Polar code. Currently, the 4G LTE technology can reach download speed of 12 Mbps. So in using Polar code, the download speed can be a lot faster than using the LTE technology. The objective of this project is to simulate Polar code under different channel environment, and also has to plot bit error rate and frame error rate at the end for different channel condition. Also, it has to be very fast. It has to be faster than the current MATLAB version. So the main concept behind this project is that we will have an K bit as an input information bit. It will go through a Polar encoder and will produce an N bit as an output, and then it will experience a channel condition. For example, it can be AWGN, it can be BSC channel, it can be BEC channel as well. And at the end, the output, which is Y here, will go through the Polar decoder to produce the final decoded message U. So in Visual Studio, it will be represented as initialize PC, P encode, auto output of channel, and P decode. For this project, there will be three predefined supported channel. The first channel is AWGN channel, which is additional white Gaussian noise channel. The second channel is binary symmetric channel, and the third channel is binary erasure channel. User can can modify the code to support more channels. This is an example outcome. I will discuss all the outcomes later in the following slides. This is only for AWGN, and this is bit error rate of AWGN channel. As we see at 0 SNR, the bit error rate is quite high. As the SNR increase, the bit error rate goes lower. So this is frame error rates. Similarly to bit error rate at 0 SNR, it will have a very high frame error rate. As SNR goes higher, the frame error rate goes lower. Okay, now I will go into details on what each function do and what are the expected outcome of each function. So in this simulation, user can change many key variables to do different simulation. The two most important variables are n, which stands for block length, and K, which stands for message length. User can change these two numbers at the start of the code. You will see a little define at the start, and you can change it to the power of n number. For main structure, user can change the following parameters to perform different simulation. For channel string, user can input AWGN, BSC, BEC, which is the 3 supported channel I mentioned before. Here's a reminder that it is case sensitive, so make sure you input upper cases for it. For channel state, it defines different channel condition. You can for different channel, you can input different numbers. For BEC, you can input 0.01 or 0.1 or 0.2, as it stands for different channel condition. Upper range and lower range and steps and iteration, they are mainly for plotting. So if you want to simulate, if you want to plot plot the result be at a bit error rate and frame error rate from certain range, you can use this function. If you would like to do all the functions individually to see how they perform in certain condition, these are you don't have to input this. So for simulation, the system will firstly perform initialization for Polo code. Firstly, it will detect the channel string to detect whether it's AWGN channel, BEC, or BSC. Then it will initialize the table using Bhattacharya parameter and fill out the Z table. Then it will sort the Z table in ascending order. It will call then it will call PCC, which is frozen lookup table initializer, fill out the frozen lookup table. After that, it will call reverse bit to detect detect how many zeros or how many ones from most significant bit. So for different channels, there will be different Bhattacharya parameter. Here is how they are calculated. Next step is the encoder. So from initializer, there will be a frozen lookup table. The first step in the encoder is load all the frozen lookup table, all the frozen bits, and detect the negative ones and replace all the negative ones by message bits. How we generate the output is to use a kernel to generate the output message. Here is the kernel. It's a binary kernel. We call it as an F. So the binary kernel is a 2x2 matrix. If we take the Kronecker product of this matrix by itself, you will get an 4x4 matrix. If we take the Kronecker product again, we will get an 8x8 matrix. Here is an example of the encoder. If n is equals to 8 and k equals to 5, information bit indices is number 1, 3, 4, 5, 6. Since 8 is equals to 2 to the power of 3, then we'll take the Kronecker product of f by 3 times and times it by information bits, and the x will be the output. So on the graph below, we can see that 0, 2, and 7, they are not information bit indices. So D0, D2, and D7 will become 0 as they are frozen. So this is how frozen bits work, and this is how the encoder generates an encoded message. The encoded message will then go through a channel block. In this channel block, the encoded message will experience different channel condition. the channel block function will firstly detect the channel string to detect whether if it's AWGN, BEC, BSC. For AWGN channel, the function will use rand_n, which is stand for normal random number from normal distribution, and represented as random white noise, and to add it to the encoded message. And for BEC and BSC, it will call rand, just normal rand function to simulate the different channel condition, and then the function will output the noisy message. The noisy message will then go through decoder block. The decoder will be using successive cancellation decoding. It will detect channel string first and use channel state to initialize LLR, which will give LLR 0 the first value, and then it will call p decodes underscore LLR to run two-way recursive function for AWGN BSC channel. For BEC channel, it will call a different function which is called p decode BEC, and then it will output a decoded message. So the decoder will be using the two-way recursive algorithm below. On the left-hand side, the function will be using bits to calculate to the right, and on the right-hand side, they will be using likelihood to go to the left-hand side. Decoder function will also generate a d-hat array by constantly update likelihood and bits. Once all likelihood and bits are updated, at all elements of rows and table when it's equal to -1, which is indicate it's a information bit location, substitute all d-hat value into that location, and that will give us the decoded message. After successfully decode the message, the function, the simulation will generate bit error rate and frame error rate and output into a .dat file. You can use any third-party plotting and software to plot them. Project conclusion. Here are some results. This is for AWGN channel. The simulation condition n equals 128, k equals 64. This is bit error rate versus EBNO from 0 to 2, and with a step of 5 and iteration of 1000. This is the frame error rate versus EBNO value. As we can see, for AWGN channel, the higher the EBNO value is, the lower the bit error rate and frame error rate will be. This is the simulation result for BSC channel. The plot is bit error rate versus different channel state P. And this is the frame error rate versus the channel state P. As we can see, the higher the channel state P is, the higher the bit error rate and frame error rate will be. This is a simulation result for BEC channel. The plot here is under simulation condition n equals 128, k equals 64, range from 0.3 to 0.4 with 6 steps and 1000 iteration. This is the bit error rate versus channel state P. And this is frame error rate versus channel state P. So as we can see, the higher the channel state P will be, the frame error rate and the bit error rate will increase. Also, I've done a runtime analysis. All the simulation ran with my desktop at home. These are the configuration for my PC. For same parameter, AWGN with n equals 128, k equals 64, MATLAB code will run 141.43 seconds, and the C simulation will only run for 30 seconds. Project conclusion. In this project, I successfully simulated a polar code under different channel condition and plot bit error rate and frame error rate. C simulation is better for large k and n numbers, and it is also faster for large iterations. Thank you very much for listening to my video presentation. If you have any question or any inquiries, please send me email. My email link is on the screen, or comment below. I will get back to you as soon as possible. Thank you very much.